school is for digital signal processing and its application. Okay, as there are 4 hours with me, so we can gradually proceed. We'll discuss about the digital signal processing, a little bit fundamental, although you have covered some fundamentals of the digital signal processing. Then what are the techniques of different digital signal processing in the application domain? And again we will do a little bit application on electrical side, a little bit application on the your biomedical sides also. And then we will go for the subcomputing technique, whatever Patnaik has told regarding the PSO. Then how to integrate all this. कैसे एक अच्छा खिचड़ी बनाए last one, so everybody will be happy, isn't it? Okay. So coming to directly to the topic, this is the DSP and its application, and already you have covered a little bit on the Fourier transform. Okay, so we will go to the other technique like STFT, WT. Have you heard this? STFT, short time Fourier transform. WT, the wavelet transform. You might have read this. Okay. Then a new technique on which we are working is known as ST, that is S transform or Stockwell transform. Then what now? And this application to the non-stationary power signals, non-stationary biomedical signal, and etc. So motivation, now first thing, while going for the signal processing, there are 3 steps. First step is signal acquisition, isn't it? Either it is a biomedical signal, or it is an electrical signal, or a communication signal, or the vibration signal from a machine. What type? Many type of signals are there. So first thing is the prime objective is to acquire the signal. You see, when you are doing research, that is separate thing. You generate a signal by writing a mathematical equation, V equal to V max sin omega t cos omega t. But it is not the case in practical field. Suppose there is a vibration, you put a vibration sensor, so from the vibration sensor you have to gather the data. Similarly, I want to take the electrical signal. Okay, so you put appropriate voltage sensor or current sensor to get the electrical signal. Similarly, for the biomedical, you have the ECG machine from where you will get the signal. So first prime important thing is signal acquisition. How to acquire the signal for the specific purpose. You know what's your purpose, why you are acquiring the signal. You see, the same electrical signal, acquiring for some purpose like you want to monitor the health of a machine, or you want to monitor the health of a distribution system, or you want to monitor the health of a transmission system. Okay, the aim is different. So the condition in which you will acquire the signal is also different. That we will discuss. So first part is signal acquisition. So once you have the signal, then you see how you are acquiring the signal by some instruments. Then the nature of that signal is maybe sometimes contaminated with noise. For example, I am taking, when we are acquiring a biomedical signal like ECG or the heart or the brain signal, that is EEG. So what happens in that? Those signal frequency range is hardly 5 Hz to 24 Hz. Okay. But how you are acquiring a signal? By a machine which operates at 50 Hz. So there is an interference of this 50 Hz signal on that particular signal. You might have experienced the same thing. Suppose if you tune your radio behind a transmission line, there is some sound is coming because of the electromagnetic interference. Because the magnetic wave which is produced by the transmission line interferes with your communication circuit, isn't it? So in that case, the signal gets contaminated with noise. So now the question is, what is the noise? Anything not interest to your signal is known as a noise. Suppose I am working in power, my interest is 50 Hz. Any frequency more than 50 Hz, of course I am interested up to certain harmonic, but beyond that, those are treated as a noise. Okay, you are interested for this biomedical signal, whose range you know that to 5 to 24 Hz. So 50 Hz signal is a noise in that case. So noise is a relative term. When you define noise, the signal which you are interested for, which is wanted, that is your true thing. The other which is there present, that is treated as a noise. So it is just like a fuzzy definition. How you define noise? It is not always the same. It depends on the application area. Clear? So now once we are capturing the signal which is already contaminated with a little bit of the noise. So second part, first part data acquisition, the second part is signal condition. Any application you will see, you will find the signal conditioning, the second step. What is signal conditioning? Sometimes this may happen that the signal which you are acquiring is of very low strength. Okay, then what you want that signal of a very high strength. So simply you put a amplifier so that the signal will be amplified, isn't it? So same thing happens. Similarly for the noise removal, whatever the signal you are having, you know that your signal may contain a little bit of the noise, so you want to filter out those noise. So those aspects, the second aspect is signal conditioning. Then in the third step, now you have the pure signal to play with. Okay, so when you have the pure signal, let's see, if I will tell you, okay, this is the ECG signal, can you know anything? कुछ पता चलेगा उसको देख के क्या हुआ है क्या नहीं हुआ है? So who will know it? The doctor who has the knowledge on that, he will know it, isn't it? I will give you a vibration signal of a machine. Can you tell whether my machine bearing is defective or my machine is okay? No. The person who is working. So again the third part is from that signal how to extract important, useful information. Clear? So once you have a raw signal, that is blind. We are blind. We don't know the signal, the nature of the signal. Okay, as long as it is a sine signal, you know that this is a sine signal because you are working in power. Okay, but if you look into an ECG signal, if you look into an EEG signal, if you look into a vibration signal, you are confused. You don't know what is the nature of this particular signal. So the third aspect is extracting important information, extracting hidden information from the raw signal or the raw data, which is a little bit part of the research of computer science, like data mining. Okay, so data mining is nothing. You have a mine, but you have to find out from the ore. You have to extract the main, either it is gold or something like. But ore is mixed with many type of things. So that concept is the data mining. You have a volume of data, but to know about those data, you have to extract the important hidden information from the data. How? By means of the signal processing techniques. So there are different signal processing techniques which can be applied to your raw signal to get important information. Okay, so we will discuss about that. Then the fourth step, okay, you have now information. So how to extend that to another? Suppose you have taken ECG signal of 100 persons. Out of 100 persons, 50 are male, 50 are female. Or 30 male, 30 female and 30 of another age, some kid, male, female, like that. Because all ECG signals are not same nature. आप अभी इसी सिग्नल मेरे को दे रहे हैं, I will take the signal and भाग के I know और signal. That is different. Okay, so once you are extracting the important information from the signal, again the rest part is identification or classification. Whether the ECG signal now what I am getting from a patient, okay, why I am taking that signal? देखने के लिए थोड़ी ले रहा हूँ. Why I am taking that ECG signal? Because I have to diagnose. I have to diagnose whether this signal corresponds to any defect in the person or not. That is the meaning. Okay, so if that is the meaning, so the first step comes the classification. You have to classify. When I am talking of the classification, you have to classify whether there is a defect or there is a no defect. Whether there is a defect in the machine or there is no defect in the machine, I can know from the vibration data. Okay, so the first step, once you acquire the signal, once you process the signal by signal processing technique, once you have the important information features from the signal, then you apply a classifier. Then in this classifier, there comes different type or different nature of the classifier. We will discuss also that thing. So among these all these four steps is complete. So this whole thing is a data research, so to say, or the whole thing is a package given to you. Starting from signal processing fundamental, starting from the feature extraction, then the classification by neural network, by fuzzy logic, by Bayesian classifier. There you can apply your genetic algorithm, PSO, to select the optimal features. What are the optimal features? Whether I have a heart problem, the problem can be detected only by ECG signal, or the doctor has to take again my blood sample for test, urine sample for test, or any other test. Then there are so many tests, so many features. What are the optimal features? What are the optimal symptoms to identify a particular disease? Are you clear my point? So how to get those optimal? There are plenty number of features. So to extract the optimal features from that, you have to look into some optimization technique. Now you are playing with GA, PK or PSO or bacteriophaging or ant colony or whatever, we will discuss that again. Okay, so this whole thing becomes a intelligent system. Whether you are developing an intelligent diagnosis system for medical purpose, whether you are developing an intelligent diagnosis for the condition monitoring of any electrical machine, whether you are developing an intelligent diagnostic system to monitor the health of your building, whether it is okay or it will collapse after some time or something like that. So all these things, or you are monitoring the track of railway track condition monitoring, completely the package is the signal processing and its application. Okay, so when I am going to the rest part, I will not go to the slides because there are 300 something slides, we can cover all these things. So first thing, as I have already told you, we will discuss from signal acquisition. So signal acquisition is very simple, you know that it is in fact I have discussed by many of the speakers earlier, by simply sample and hold circuit. So you have a continuous signal like this. You have a continuous signal like this. So to get the signal in the digital domain, because you have to process in the computer, so you have a analog to digital converter. Okay, how accurate your signal will be captured depends upon which factor?
Sampling rate.
No, one is the sampling rate. If I am sampling this, you see, these are the different points you are getting. This is just you can treat it as a continuous signal xt is sampled in terms of xn, where n is the sample number. So you imagine just like a switch which is closed at t equal to 0, t equal to 1 into ts, t equal to 2 into ts, 3 into ts. So like we are getting. So for this purpose you require a sample and hold circuit. Okay, and particularly this is achieved in hardware domain by analog to digital. So there the resolution of the ADC is plays an important. Whether it is a 8-bit AD converter, 16-bit AD converter, 32-bit AD converter. Okay, that depends on the resolution. Because what is the resolution? The particular sample value you are taking. You see, this sample value may be 0.0034. So it will, the number of binary bits, the bit we are taking 8-bit converter. That means it will represent the whole range, either 1, 1, 1, 1, 1 up to 8 bits. Isn't it? 0, 0, 0, 0, 0, like that. Again you have negative value, so another component you require, so one component is gone. Whether it is 1 or 0 it is negative, we are not going into the detail into that. So the accuracy of the ADC converter depends upon your bit. So when you are, even if for your lab you will give the order for any ADC converter, they will ask you what is the resolution you want. And the more will be the resolution, the more will be the cost of that particular product. Clear? So once I am sampling this signal, I am getting my digital signal. So this is the simple version representation. A continuous form A cos omega t plus phi. When we will go into the discrete version, it is A cos omega. N is the sample number, Ts is the sampling time. Okay, so N0 first sample, N1 second sample. So like that. But when you are doing in MATLAB, you see MATLAB does not take 0 index. So you have to start from index 1. Clear? So this is the simple concept of this sampling. Now see, this is a sinusoidal. Now here I just want to give an emphasis on why sampling frequency is an important concept. You might have known what is the concept of the sampling. If you want to sample a signal, what is the concept?
Twice the.
No, how to choose the sampling frequency?
Twice the.
Yeah. Question is, first you have to look into the bandwidth of the signal. What is bandwidth? That is the frequency range on which you are interested. Okay, suppose I am a power person, I am working in power. Let I am interested up to 20th harmonic. So if I am interested up to 20th harmonic, my frequency range of interest starting from 0 to 20 into 50, that is 1 kilohertz. So I must sample it by more than 2 kilohertz or 2 kilohertz according to Shannon sampling theorem. So similarly, if I am working in biomedical signal, my interest is simply up to 25 hertz. So I may sample at 50 hertz, 100 hertz, 200. But that we will again see. There may come 3 possible combinations. Either oversampling, you are sampling at a very high rate. You see, if you will sample at very high rate, then the number of points you are getting of the signal are very large. So the memory requirement for that is also large, isn't it? Again, the computation on those volume of data is also large. So again, second thing, if you are sampling at very low sampling rate, what is the demerit? We have to see. So we will consider those three cases, okay, with different sampling frequency. See, now if you have a signal, if you check, this is a signal. If you are choosing different sampling frequency, what will happen? For the same length of the signal, we will get different number of data points. Suppose you are sampling it, it's what is the time period? If it is a 50 Hz sinusoid, the time period is 20 milliseconds. Suppose you are taking the sampling time 2 milliseconds. So for one cycle of the data, you are getting only 10 points. If you will sample at 1 millisecond, you will get 20 points. So that is the first point. With different sampling frequency, sampling of an analog signal will give different discrete sequence. That means either you will give a discrete sequence of length 10 or length 20 or length 40 or length 50. Then sampling of different analog signals may yield the same discrete sequence now. Okay? Then third one, the sampling frequency must be employed in order to reconstruct the original analog signal. That is the important thing. Why reconstruction of a signal is important? Now see, suppose I am sampling this signal and I am taking only one sample here, one sample at the peak, one sample 0, then one sample here, one sample here. When you will reconstruct this particular signal, reconstruct means you want to see what is your original signal, then what will happen? You are getting a waveform of this nature. Now your sinusoidal signal becomes a triangular one. Again, suppose you want to sample this signal at 10 milliseconds, because your time period is 20 milliseconds. So it will sample at 10 milliseconds. So what are the data point you will get? This is one data point, this is one data point, this is the other data point. And if you reconstruct the signal, it is nothing but a DC, DC of 0. So the originality of the signal is lost, isn't it? So sampling frequency plays an important role. That's why in the very beginning I have told you have to look into your signal, on which area you are working, what is your interest frequency range of the signal, that is bandwidth of the signal. Then once you know the bandwidth of the signal, you have to choose a proper sampling frequency for that. Clear? This is from the application point of view. Then this is the question now I want to discuss. What happens if the sampling is lower than the request sampling rate? According to Shannon sampling theorem, if you are interested up to the bandwidth of the signal is, let us, f, you must sample it fs must be greater than equal to twice of the f. So this twice f is known as the request sampling rate. So if my sampling rate is lower than the request sampling rate, what will happen? If it is higher than the sampling rate, what will happen? So that we will see. You might have heard this word, aliasing effect. So what is this aliasing effect? Why it comes? Can you tell me?
When it is less than twice of.
Why? My question is why? Why it comes? Yes, we know. If I am sampling a signal less than the request rate, then there is a aliasing. What
Loss.
is it?
Because of the loss.
Loss of information bandwidth.
Right. See that how it is happening. I will just give a simple example. Now you consider these three signals. Xt is a signal. This is a very simple example. Xt, a cos 2 pi f0 t plus phi. Fine. Another signal yt, a cos 2 pi f0 plus lfs into t, where fs is your sampling frequency. L is a discrete number. So when L equal to 0, xt equal to yt. When L equal to 1, now it becomes f0 plus fs plus phi. And the third signal is a cos 2 pi minus f0 plus lfs t minus phi. So these are the three signals. Okay. Now all the signals are sampled at what sampling frequency? Fs. I am sampling these three signals at a sampling frequency of fs. Let us look into that. So what will be your first signal? A cos 2 pi f0 t. So t will be replaced by a into ds plus phi. So what is the frequency? Frequency in that case is f0. Your original frequency of the signal is f0. Come to the second. Second signal क्या था?
Minus.
Cos 2 pi f0 plus lfs. So I am writing now A cos 2 pi f0 plus LMS into t will be replaced by MTS plus phi. Make a little bit mathematical analysis. So finally you are getting A cos 2 pi f0 MTS plus phi. That is nothing but xn. Now see, these two signals, are they of same frequency? Xt is a signal whose frequency is f0. Yt is a signal whose frequency is f0 plus LMS. But when both are sampled at a frequency fs, both are yielding the same sequence. Are you clear my point? Both are yielding the same sequence or same sample points. Let us go to, but actually what is the frequency of this second signal y? f0 plus LMS. Are you clear? Next, w with like this. Again this also is a same sequence, minus f0 plus LF. Now are you clear this concept? So xn, the discrete sequence which you are getting. Now I have taken three signals. One signal of frequency f0, another signal of frequency f0 plus LF, another signal of minus f0 plus LF. If I am sampling these three signals at the same sampling rate fs, I am getting the same discrete sequence xn. Okay, so the question is xn might be the same samples of these three signals. However, only one of the above is the original signal. Are you clear? Only one signal xt is your original. The other with the secret frequency of LFS and minus LFS. Are you clear? So that's why this is the effect of aliasing frequency. So for a signal f0, what are the aliasing frequency? If a signal of frequency f0, you are sampling at a sampling rate of fs, the aliasing frequencies are f0 plus lf minus f0 plus lf. Are you clear now about the concept of aliasing? Okay, so this is the aliasing. So due to this, what will happen? When you will see in the frequency domain that particular signal, these aliasing frequency will appear. So it will make a confusion whether your signal is f0 or f0 plus lf or minus f0 plus lf, because the signal is of f0. The signal is of f0. You have to choose fs in such a manner that these aliasing frequency will be always there, but it should not come in the bandwidth of the signal. Otherwise, if all this, suppose in this case, let f is 100 Hz, for example, f is 100 Hz, your f0 is 50 Hz. So what is your aliasing frequency? 50 plus 1 into 100, 150 will be aliasing. Then minus 50 plus 100, 53. Okay. Again you take twice of that, so 250. But whether you don't know whether your signal contains 150 Hz or it is the aliasing frequency. So how to know it? Are you clear at this point? So that is the main problem of this aliasing frequency. Okay. So I am just showing you the detail because as I have to discuss many things. I will take an example, show you the effect of aliasing. So this is a signal I have taken, A cos 2 pi 100t plus pi. Okay, a simple example. So here it is a signal of frequency 100 Hz. And let us sampling this frequency at 1 kHz, 1000 Hz. It exactly more than twice of your frequency interest, because your frequency interest is 100. So 200, it is quite more than that. So if it is quite more than that, now this is a sample signal A cos 2 pi 0.1 n plus pi. What is 0.1? 0.1 becomes the normalized frequency because 100 divided by 1000, f by fs. So it is a normalized frequency. So what is your aliasing frequency in this case? Plus minus 100 plus minus 1000 n. F has into that? One is f plus lf, another is minus f plus lf. So these are the aliasing frequency. Fine. Now let us see what happens. Now if I am sampling this, remember, what is my signal? What is my signal? 100 Hz. What is my sampling frequency? 1000 Hz. So if you are sampling the signal at 1000 Hz according to the Quist criteria, according to Sharon sampling theorem, you will get the information of the signal up to half of the signal, half of the sampling rate. Because if you are sampling at a phase, the reverse way. If you are interested up to 8, you have to sample more than 4 fs. So if you are sampling at a rate of fs, you will get the frequency information up to fs by 2. So that's why the rectangular window which I have drawn, you see up to what frequency? See the left part, up to 0.5. What is 0.5? 500 hertz. You are sampling the signal at 1000 hertz. You will get the information up to 500 hertz. So 500 hertz in per unit is 500 divided by 1000, that is 0.5. So this is your bound. Okay. In this case, what is your aliasing frequency? 100. What is your aliasing frequency? 100 plus 1 into 1000, and then minus 100 plus 1 into 1000. So what is this aliasing frequency? 1100. In per unit 1.1. This is 900. So now see, these are the two aliasing frequencies which are shown you at 0.9 and 1.11. But this aliasing frequency lies completely outside the Nyquist band, because you are sampling the signal at a very high frequency. So those aliasing frequency, when you look into the effective Fourier transform of the signal, those frequency will not enter into the boundary of the Fourier transform. So be clear in your mind, aliasing frequencies are always present. Clear? But whether it will be observed in the Fourier analysis or not depends upon your sampling frequency. So in this particular case, although my signal interest is 100 Hz, but as I have sampled it at a very high sampling rate, nearly 10 times 1000 kHz, the aliasing frequency are completely outside my boundary of 500 Hz. Any doubt on that? So this is the simple concept of the aliasing. Let us go to the second.